Welcome to this exciting course on chemical kinetics. Imagine we are time detectives, seeking to unlock the secrets of reaction rates. This introductory image presents our mission, learning to follow, step by step, the evolution of chemical transformations in aqueous solution. We will use tools like stopwatches, test tubes, and graphs to understand how the concentration of reactants and products changes as the seconds tick by. This is the beginning of an adventure where chemistry meets physics to measure the invisible. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's dive into the mystery of chemical speed. In nature, reactions don't all run at the same pace. We classify them into three categories. 1. Fast reactions. They are almost instantaneous, like an explosion or a precipitation. The reactants barely touch before it's already over. 2. Slow reactions. This is our favorite target. They last from a few seconds to a few hours. Why are they so important? Because they offer us a measurable time window. We can see the color change or bubbles gradually form. 3. Very slow reactions. Like rust on a nail, they take days or even years. Our goal as chemists is to study slow reactions because they are the only ones whose progress we can follow live in the laboratory documentation. But, by the way, what is temporal monitoring? It's the act of measuring the quantity, the concentration, of a reactant that disappears or a product that appears at different specific moments, all while keeping a constant total volume. Look closely at the image. We see a solution go from light yellow to dark brown. To track this, we have two main families of methods. Physical methods. They are great because they allow for real-time tracking without ever touching the mixture, like measuring color or conductivity. Chemical methods. Here, we have to take small samples, test portions at different times to analyze them, which often requires stopping the reaction in the collected sample. It's like taking pictures of a race to analyze the position of the runners. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's explore high-tech physical tools. First, conductimetry. If your reaction produces or consumes ions, like Zn2+ or H3O+ in the example, the solution's ability to conduct electricity will change. We dip a probe in and read the value live. It's clean and fast. Next, pressure. If your reaction releases a gas, like dihydrogen, H2, the pressure inside the closed flask will increase. By using the ideal gas law, PV equals nRT, we can transform a simple pressure measurement into a number of moles of gas produced. It's a powerful mathematical trick to see gas molecules forming. Let's continue with light and acidity. Spectrophotometry is an incredible visual method. We pass a beam of light through the solution. If the solution is colored, like purple permanganate, it will absorb some of the light. The more colored molecules there are, the less light passes through. It's the Beer-Lambert law that directly gives us the concentration. Next, pH metric monitoring. If acidic H+ ions are involved, the pH of the solution will vary. A simple pH meter allows us to track the disappearance or appearance of acidity. These methods are perfect because they don't disrupt the chemical system. We simply observe nature at work. Now, here is a classic and rigorous technique, volumetric titration. It's a chemical method in 3 key steps. Step 1, extract. We draw a small volume, for example 5 milliliters, from the reaction mixture. Step 2, chill, the quench. This is the crucial step. We plunge the sample into ice water. The cold abruptly halts the reaction. It's as if we froze time so that the composition no longer changes while we take our measurements. Step 3, titrate. We use a very fast assay reaction to determine the exact quantity of the chemical species at that precise moment. It's a more laborious method than electronic sensors, but extremely precise and fundamental in chemistry. Let's now learn how to read evolution curves. It's the graphical language of kinetics. On the vertical axis, we have the amount of substance in moles, and on the horizontal axis, time. Observe the 2 curves closely. The red curve goes down. These are the reactants being consumed. The blue curve goes up. These are the products being formed. Remember, the system evolves until a horizontal plateau is reached. This plateau means that one of the reactants is completely exhausted, the limiting reactant, or that equilibrium is reached. The slope of these curves gives us crucial information. The steeper the curve, the faster the reaction is at the beginning. When it flattens out, the reaction slows down. Let's get into the mathematical heart of the subject, the volumetric rate of reaction. The formula is V equals 1 over V times dx over dt. Let's break it down together. V is the total volume of the mixture. X is the progress of the reaction in moles, and dx over dt is the derivative of the progress with respect to time. Graphically, this rate corresponds exactly to the slope of the tangent to the curve at a given instant t. Look at the graph. At the beginning, the tangent is very steep. The rate is maximal because the reactants are plentiful. As time passes, the curve flattens out and the slope decreases. At the end, the tangent is horizontal. The rate is 0. The reaction is over. It's like a car slowing down before stopping at a red light. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content.
Here is a very handy indicator, the half reaction time, T1/2. By definition, it's the time required for the progress of the reaction to reach half of its final value, X max over 2. How do you find it? It's simple. 1. Locate the final value, X max, on the vertical axis. 2. Divide this value by 2. 3. Project horizontally to the curve, then drop down vertically to the time axis. The resulting point is your T1/2. Why is this useful? It allows us to compare the efficiency of different reactions, or the influence of external factors. It's a sort of temporal ID card for the reaction.
Can we control this chemical clock? Yes, thanks to kinetic factors. These are the levers we can pull to speed up or slow down a reaction. 1. Temperature. The more we heat things up, the more the molecules become agitated and collide violently, which speeds up the reaction. Conversely, ice stops everything. 2. Concentration. The more reactants there are in a small space, the more chances they have to meet and react. It's like a crowded dance floor. 3. The catalyst. It's like a magic wand. It's a substance we add that massively speeds up the reaction without being consumed itself. It offers a chemical shortcut to go faster. Let's look at a concrete case, the reaction between dichromate ions and bromide ions. First of all, we write the redox half equations to obtain the overall equation. Carefully note the stoichiometric coefficients. Next, we set up the advancement table, ICE. Initial state, we have our quantities C1V1 and C2V2. Change state, this is where the magic happens. We subtract x multiplied by the coefficient for the reactants, example minus 6x for Br minus, and we add x multiplied by the coefficient for the products, example plus 2x for Cr3 plus. And finally, final state. We replace x with x max. This table is your map to navigate the rate calculations. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Demonstration: how to calculate the rate by tracking a product. Let's take the Cr3 plus ions. 1. We read in the table that the amount of Cr3 plus is 2x. Therefore, its concentration, Cr3 plus, is equal to 2x divided by V. 2. We isolate x to find the relationship. X is equal to Cr3 plus times V over 2. 3. We differentiate with respect to time. Since V and 2 are constant, they come out of the derivative. We get dx over dt equals V over 2 times d Cr3 plus over dt. Finally, we substitute into the rate formula. V equals 1 over V times dx over dt. The result is magnificent. V equals 1 over 2 times d Cr3 plus over dt. We can therefore know the rate of the entire reaction. What if we followed a reactant instead? Careful, there's a little catch. Let's take the bromide ions, Br minus. 1. We establish the relationship. Br minus equals C2V2 minus 6x divided by V. By isolating x, we find a slightly more complex expression. By differentiating, the initial constant C2V2 disappears. We end up with a minus sign in front of the result. Why this minus sign? Because a reactant disappears, so its variation, dBr minus over dt, is negative. The minus sign in the formula compensates for this so that the final rate is indeed positive. In physics and chemistry, a reaction rate is always a positive quantity. Here is the golden rule, the ultimate summary for any reaction. Of the type alpha A plus beta B yielding gamma C plus delta D, the volumetric rate V is equal to the derivative of the concentration of any constituent divided by its stoichiometric coefficient. For reactants A and B, we put a minus sign because they disappear. For products C and D, the sign is positive because they appear. It's the universal formula that links all the actors of the reaction together. Learn it well. It's your master key. Congratulations! You've cracked the code of chemical time. To summarize our investigation, the tools: pH meter, conductivity meter, spectrophotometer, titration. The evidence: the evolution curves that give us the rate, slope. The decoders: our mathematical formulas, V, T1/2. The controllers: temperature, concentration, and catalyst to master the pace. You are now ready for your lab experiments. Keep exploring and questioning the world. You're doing great work. Gondwaret, Star Scientist.